Hello everyone, my name is Yutaka Tokuda from University of Sussex. I'd like to present FlowKit crafting tangible and interactive electrical component with liquid metal circuit. This is a joint work with Deepak Ranjan Safu and Matt Jones at Swansea University, Sriram Subramanian at UCL, and Anusha Witana from the University of Sydney. DIY Tangible Computing Toolkit have changed learning experience in electronics more playful and creative with interactive engagement. However, it is still hard to craft DIY electric component and playfully learn electronics principle. For instance, it's difficult to interactively and visually explore the law of resistivity and the two-plate capacitor model with the same DIY method. Researchers investigated DIY method to build various analog electric components with high-conductive liquid metal. For example, Wu et al. Used liquid metal to create 3D printed passive components, and Nageo et al. Demonstrated various flexible sensors by sealing liquid metal circuit with silicon. Meanwhile, other studies show the usability of fluidics to make tunable electrics and interactive materials. As example, Gerard et al. Utilized the flow of conductive liquid as dynamical switch, and Moore et al. Explore various fluidic mechanisms to build analog fluidic sensor and display. In this paper, we introduce FlowKit, which is a DIY toolkit to build interactive electric component with liquid metal fluidics. FlowKit uses analogy of conductive liquid flow and electric current for playful learning basic electric component. For instance, we can easily build and explore tunable capacitor by controlling liquid metal flow. As a design concept, FlowKit follows tangible visual electrical analogy, where tangible inputs are directly reflected in both visual and electrical change as output. Let me explain this with an example. This image shows dynamical liquid switch composed of sealed liquid metal in a reservoir, transparent liquid channel, and LED as electrical output. To explore switching mechanism of electronic circuit, we can press liquid metal to deform and visually probe the electric contact with open LED circuit. Likewise, we can demonstrate electrical state changes by adding another reservoir along the channel. Conductive liquid metal droplet moves to another reservoir by giving pressure and works like the binary switch to turn on multiple LEDs. Furthermore, we can interactively explore electronics principle with visually tunable liquid electric component. For example, we can build tunable resistor with high conductive liquid metal and low conductive ionic solution, and demonstrate the law of resistivity by adjusting the liquid volume ratio. Next, let me explain FlowKit workflow. There are three main steps. The first step is design and preparation of 3D printed stamps and molding material. FlowKit uses familiar stamping process to design liquid electric components. The second step is fabrication process of liquid electric component. There are three hands-on processes: imprinting substrate, sealing imprinted liquid channel, and infusing conductive liquid. The last step is tangible interaction to probe the functionality of the fabricated liquid electric component. Let me start from design and preparation step. To design FlowKit stamp, there are three types of elements, namely fluid element, fluid I/O, and electrical I/O. Fluid element design liquid channel, reservoir, resistor, and capacitor. Fluid I/O imprint fluid port for infusion and drain process. Electrical I/O design wiring terminal to probe electrical change. Design of fluid element requires to model fluid properties, such as pressure and hydraulic resistance, as well as electrical properties, We created FlowKit Stamp 3D CAD toolkit, which informs these values from stamp geometry and liquid parameter, and provide graphical user interface to tune and assemble template stamp elements. The toolkit can export the design stamp as a STL file to 3D print for the following imprinting process. To help manual imprinting, we optionally provide a stamp holder and stamp support pillar to control imprinting depth. As a molding substrate of the FlowKit, we use Blu-Tack, which is commonly available pressure-sensitive adhesive silicone. Blu-Tack works like the clay to imprint fine texture and very sticky to the tape. We wet Blu-Tack to reduce adhesiveness and place it between seams, then use a clay roller machine to make even surface with specific thickness. Next, I will move on to the fabrication step. Since Blu-Tack is very adhesive to 3D printed stamp, we must coat the surface with fine powder, such as cornstarch, before imprinting. We can restore the Blu-Tack adhesiveness by cleaning the surface with water. If imprinting fails, we can recycle Blu-Tack through a clay roller machine. The next process is sealing the imprinted channel with a tape and prepare a fluid I/O terminal for infusion. After placing the washer as a gasket at the terminal, we seal the imprinted area with a transparent duct tape. We use a soldering iron to open the terminal, then glue magnet link on the top. The sealed component is easily cut out with a hobby knife. Fabrication process is completed by infusing conductor liquid through a Fusion I/O terminal. A custom magnetic tube adapter is designed to quickly attach and detach a tube to the fluid I/O terminal. We use a Tygon tubing for smooth fluid flow. As conductive liquid, we tested highly conductive EGAN liquid metal and low conductive sodium hydroxide solution, which also works as a lubricant of liquid metal by preventing the oxidation. Finally, we discuss the robustness of tangible interaction. The robustness of tangible interaction depends on the substrate material. We found Blu-Tack likely yields above a force of 50 Newton, which is regular finger pressure force. To enhance the elasticity, we mix the Blu-Tack with some plastic elastomer, Oyumaru, and gain significant improvement of yielding strength with a trade-off of adhesiveness. Let me introduce interactive applications. Utilizing elastic deformation of liquid metal with surface tension, we can craft a dynamical liquid push-button switch by imprinting a set of reservoir and a channel. Likewise, toggle switch is easily made by imprinting a second reservoir for liquid metal relocation. We can apply these fluid switching mechanisms to design various digital logic gates. Analog electric component is another application. We can create variable resistor by infusing different volume of two conductive liquid. As the law of resistivity simulates, resistance decreases proportionally to the volume of high conductive liquid metal. We can also design a variable capacitor by controlling liquid metal flow between ITO electrodes. We found linear increase of the capacitance with respect to liquid metal area as the equation for parallel plate capacitor cells. We can also use force-sensitive liquid deformation as pressure sensor after calibration. As a limitation, maximum fabrication size depends on the clay roller size, which is around A4 paper size. Considering robustness, 1 mm to 2 mm square liquid channel is recommended with larger depths. Although liquid metal is safe, sodium hydroxide solution is caustic and better to dilute for safety. In conclusion, we propose FlowKit, a DIY toolkit to craft electrical component with liquid metal. We explore tangible visual electrical analogy for playful learning electronics principle. We technically evaluated FlowKit concept with applications. That's all my presentation. Thank you for your attention.